you're fine with basically trusting Coinbase with everything, that's fine. I think a lot of the developers don't want that because they understand that either tomorrow, because of corporate needs, or if not that, then whenever the Democrats come back in power and decide to take it out on Brian and his folks, it won't be fun to be building on Base, right? Things, will just be blocked. You cannot do this, So if you want centralized, sure, but then you don't really need blockchain.
All right. Hello, everybody, to another episode of Accelerate. Today, I have with me the godfather of ZK, Eli. Eli, how are you doing?
Very good. Great to be on this. Thank you for having me, Mert.
Of course. Well, so I want to roughly frame the conversation for the audience for what I want to talk about personally as a selfish person. And that is going to be, I want to talk about obviously ZK, some of the nuances, you're a co-founder of Zcash, working at Zcash, and then StarkWare, and then maybe privacy and how you see the combination of these things evolving in the future. What is the long term? What is the short term? What is the medium term, etc. So let's introduce people. I'm sure everybody in crypto has heard the two letters ZK in that sequence. Stands for zero knowledge. Probably people are not familiar with how familiar you are with ZK, and I'll let you kind of talk about your history there. And then I thought it would be fun to describe ZK as a professor as with three different levels of abstraction. So one would be for people who are not in crypto, one for people who are in crypto but are not technical, and then one for very technical people. Cool?
Yep. Okay, so by way of introduction, Eli Ben-Sasson, I'm co-founder and CEO at StarkWare. I was also a founding scientist of Zcash. I started my career as a mathematician, and everything changed when I went on the podium at the Bitcoin conference in San Jose in 2013. And I was the first to suggest to the audience there that ZK is the solution to two problems of blockchain, both privacy and scalability. Ever since then, I've sort of transitioned from math papers into market momentum, co-founded Zcash and then StarkWare. So now, what is ZK that everyone's talking about? I'll try to explain it at three different levels. So first of all, for a layperson, I would say we're talking about proofs. Now, what is a proof? When you go to a restaurant and you get a receipt at the end of the meal, that is a proof, right? It is a means to an end. You're asked to pay, I don't know, $15.30. And to convince you that that's the sum you need to pay, you're given this string of characters, right, written on a paper that basically shows the items and then sums them up, adds tax, maybe service, and reaches $15.30. So a prover, the restaurant owner, has worked in order to run a computation, and they're presenting you a statement. The statement is, please pay $15.30. And there's a proof that says you really should pay that, because if you re-execute the same computation, sum up the items, compute 15% tax or whatever it is, and then service, 20% service, you'll get to 1530. And you can do that. So you can verify the correctness of the proof. So a ZK proof is a little bit like that. It's something that convinces you that a statement is true. But the two big differences are scalability and privacy. The receipt doesn't really scale well, because if there'd be a million items, you would need to run a computation that sums up a million items. So suppose you could get somehow a magical receipt where you don't need to sum up a million entries. You just sort of sample two or three of them, and you know that everything was done with integrity. That's the scalability part, which I find more mysterious and more important. There's also the privacy part, which is a little bit like, suppose you get these things blanked out, but nevertheless, you know that the sum you should pay is correct. That's what ZK gives you. So ZK proofs are a means to an end. The end is integrity, knowing that the right thing is done and you need to pay, whatever sum it is. And the two magical properties are that the proof can be much, much shorter to verify than it would be to do the computation. And there's privacy, which means that a lot of the stuff can be blanked out and you can still know with no trust assumptions about the other party that the computation was done with integrity.
Okay, cool. That makes sense. So in general, prove that you did something without revealing the something, and then one can verify that you did it. So like one
Yeah,
example
prove
could
your
be,
integrity. That the right integrity means doing the right thing, even when no one is watching. So prove that you operated with integrity. And then you can even blind some of the inputs. Yeah, I operated with integrity. You should still pay me $15.30, even though you didn't see everything that happened.
mhm. Okay. Now let's see if I can. I'm sure there'll be engineers and some technical people, developers, etc., watching this as well. Let's maybe try to also explain it from a technical level. Like, how does this actually work?
Okay, let's try to explain. How could it be like there are two very magical properties that are happening here? One is scalability, which I always say is more mysterious. It is about, even though there could be a million steps to the computation, in order to verify the integrity of all of those million steps, and with no trust assumptions about the other party, you only sort of, sample two or three of them. So how does this magic come about? And the second magic is, how do we get to verify? Like, if I would inspect a receipt, I would learn a little bit about, like, which items were consumed, how much they cost. How could I check this thing without like learning anything? So these are two separate pieces of magic. Let's first of all talk about the scalability aspect. So the magic is, well, there's one part that isn't magical, and then there's the other part that is magical. So the part that isn't magical is related to this thing called polling or polling, right? You want to know with a very high degree of certainty what will be the outcome of an election. So, okay, you can go on Polymarket or Kalshi, okay, but the old way was you take a sample of 100 people randomly chosen, and you ask them what they're going to vote for, assuming that they were randomly sampled. You will get a very, very accurate estimate of the result. Okay, um, that's mind blowing. In fact, the level of error is independent of the population size, right? Even if you want to poll the election of, the United States president, or of China, if they were to have an election, 1 billion people or 300 million people, you don't need to go, you can ask 1,000 people. That's enough for both of these cases, because you'll get very high accuracy. So, how do we get scalability with ZK proofs? Well, we apply polling. We, instead of checking each and every step, we just poll a few random points. That's how we get the sort of the scalability aspect. Instead of checking, it's just like the scalability you get from polling, right? You don't need to go and poll every citizen in the United States in order to get a good estimate for the outcome. The really
Mhm.
magical part is, how do you prepare the receipt in such a way that that its integrity becomes pollable, right? Because if you just, if I would just take the receipt as it is with all of its lines, someone could easily cheat there, right? Just add a bunch of zeros or do an addition that isn't quite right. So there's a separate process that is about adding more and more information in a way that makes it impossible to cheat, or impossible to cheat when you poll the result. So that's how you get scalability.
Mhm.
The privacy part you get, I'll give you an analogy. Suppose there's a combination lock and I know how to open it. So, and I want to prove this to you without you learning anything about it. So I could just tell you the combination, and then I will prove to you that I know to open it, but I also revealed information. But I could also do the following thing. I could take the lock itself, turn around, open it, and present the open lock to you while holding the combination, hiding it with my fingers. And
Mhm.
then I can close it again, scramble it, give it to you, and we could do this a couple of times, right? I will convince you that I know how to open the lock, but you will learn nothing about the combination. So that's how ZK rough the privacy, the sort of shielding works. You take
Mhm.
information and you turn it, or knowledge, and you turn it into something you can do, which you shouldn't be able to do if you don't have that information. So it's a little bit like that.
Got it. Okay. That makes sense from a medium level of abstraction. Now I want to understand from a math. So I am a math major. Um, I'm sure many people probably won't be, but I do think like the math is not that unapproachable. So maybe let's look at it from a university student lens now in terms of how does ZK work? Like, what are you using? Difference between a snark and a stark, and what kind of math are we using here?
Okay, I'll try to still. Okay, I used to teach this at graduate level semester long courses, but I'll try to roughly explain for mathematicians how it is that we can even be at a situation where we poll a very long computation and how can we hide information. So, explaining how to hide information is a little bit easier. It is very similar, almost identical to the way you do something like Shamir secret sharing, which is basically okay. First of all, we move everything to the language of polynomials. And polynomials have, so I'm speaking now to the math majors. So polynomials have a lot of magnificent properties to them in so many different areas of math and computer science and engineering. Okay. One of the properties that they allow you to do is this beautiful trick of Shamir from the 70s of secret sharing, which basically says, suppose I have a secret and I want to share it, let's say, between three people so that any two of them can open it up. I'm taking the simplest example. So here's what I do. I basically think of the secret as a number, and it will be the value of a linear function of a line at zero. So it's where the line touches, hits the y-axis. Okay, that's the secret. Now what I do is I randomly choose a slope, and then what I do for each of the three people, I give, let's call them one, two, and three. So the person one, I give the value of the line that I picked a random slope and it passes through the secret. So to
Ah, I see.
person number one, I give the value of the line at one. To person number two, I give the value of the line at two. And to person number three, I give the value of the line at three. Now, here's the beauty of it. Any one of them by himself getting what he got has no information, has zero knowledge about like what is the secret, right? Because any slope could pass between the point you received. Let's suppose you're number one and I'm number two. Okay,
Mhm.
so you get no information about that secret. But if you and I combine our shares, oh, now there's a line, and there's exactly one intersection point with. So any two can sit together and compute the secret, but no one on himself can compute. So here's a case of how do you hide information using a polynomial. So a line is a degree one polynomial. If we were four people and you wanted to share it between three, you would just pick a random parabola or quadratic, a degree two polynomial. And it
What's
turns out that
what is a degree in real ZK? Like, what degree polynomial do you use?
I'll answer that in a minute. But okay, I mentioned a million steps. The degree would be a million. Well, slightly more. The degree would be a million for scalability, but for privacy, you're going to have like a million and one or a million and 10 because you want this sort of wiggle room where you want to hide information in a sort of Shamil secret sharing kind of way. So you want something
Mhm.
that captures all of the information, but has a little bit of randomness left in it. But roughly, the degree of the polynomials you're dealing with are the size of the computation you're talking about. So the degrees are going to be like in the 1,000 to 1 billion range typically. Anyway, so you get the hiding from using that property of polynomials that I don't want to formally describe right now. And for the scalability, use now I'm moving more to the EECS or electrical engineering and computer science. There's this amazing property of polynomials. They actually are the basis for amazingly good error correcting codes, and which means there's a lot of like very good redundancy that you can get by taking a bunch of numbers like a grocery receipt, like a million entries in a grocery receipt, interpolating a degree million polynomial through them, and then evaluating that polynomial not on a million points, but like on 10 million points or a billion points. And if you have that information, there's a lot of redundancy. And that is somehow, that redundancy is what is used in the polling phase of ZK Stark
Mhm.
and to give you scalability.
Wow. All right. That is an excellent explanation. That is actually simpler than I thought. I mean, obviously, you're not doing the theorems and the proofs and stuff, but the conceptual stuff makes sense to me.
Yes.
Um, how does, for my curiosity, how does this compare to MPC? Because it seems like it has some similar properties to MPC where it's
Yeah.
collaborative computation in some
Okay, so I
sense.
can explain the math level, or I can explain what is it that you get from it, like on a blockchain. So on the math level, I would say that MPC even leans deeper into the sort of privacy aspect, the Shamir secret sharing. And if you look at the early protocols, really there were some level built over the Shamir secret sharing. Like basically, what happens in a multi-party computation? I mean, there's let's start with that line. So we have like three people who have inputs and they want to compute something on it. So you sort of pass a line or a three polynomial through those folks, and then you start doing all kinds of manipulations on those polynomials, stuff like that. So mathematically speaking, I guess a lot of the advanced cryptography that is used in blockchain happens to use polynomials because they're like so magical and have so many nice properties. But now, in terms of what is it that you get from MPC and what is it that you get from ZK proofs? Okay, we already said what you get from ZK proofs. You get integrity. You know that the right thing was done even when you were not watching, and this is tremendously powerful in the blockchain space. As I said, I was the first to suggest that you can use proofs for scaling blockchains, and this was in 2013. And actually, the way it happened was like this: I was talking mostly at universities, explaining what I'm doing. And like the professors there were like, yeah, but who cares? Why are you implementing this stuff? And then I got off the podium at the Bitcoin conference in 2013, and folks like Greg Maxwell and Mike Hearn and Gavin Andreessen came and said, okay, where's the fucking code? I asked them, why do you need the code? They said, okay, here are like 5 different things we're going to implement with it. And it took me a very long time to realize why they needed it so much. It's because decentralized blockchains are all about integrity. They're about a new way to know that the right thing is done even when you're not watching. And Satoshi and then, everyone after him solved it by like having this beautiful decentralized protocol where everyone's invited to participate. But what it delivers is integrity. You know that your Bitcoin won't be seized, or you're a Solana maxi, you're a Solana or Ethereum or whatnot. Zcash, I'm a StarkNet maxi. Same thing. Um, so you have this sort of integrity thing. Now, proofs give you that integrity. They give you it with privacy, they give you it with scale. Okay, that was proofs. Now, what does MPC give you? MPC, first of all, does not give you integrity, meaning if you want to know whether an MPC computation was done correctly, well, you damn sure have to participate in it, or you have to have someone that you trust participate in it, or
Mhm,
you need a proof that
mhm,
the MPC worked correctly. Okay, so the MPC does not solve integrity at all. It does do something that could be very important. Think about an auction done on a blockchain. So, there's this beautiful NFT. You would like it to go to the highest bidder. 10 people show up. How do you run it without like front running and so on? So MPC solves exactly that for those 10 people. So they all participate, they send all kinds of stuff. And the end of the MPC is that the winner, like everyone knows exactly what they need to know and nothing but. So everyone knows, like if I was the winner, I will know that I won and how much I'm paying. If I
mhm.
was one of those who lost, the only thing I will learn is that I didn't win, and that's it. I wouldn't know who of the other 9 won, and I don't know how much they paid. So the MPC gives you beautiful privacy, but it gives you no integrity, whereas ZK proofs give you integrity for scale and for privacy.
Understood. Okay, that makes a lot of sense. And then, okay, let's maybe um, st- bring this full circle. So we have ZK there, where we can use it for integrity, privacy, and scale. We can use MPC for some subset of those, except for integrity, at least without trusting that subset of
Right.
MPC participants. And then we have two other things in privacy, which one is going to be TEEs, trusted execution environments, and then finally something that's kind of on the come up, it seems, but I'm not sure what's real, what's not, etc., which is FHE, fully homomorphic encryption. How would you also describe those and put them into this image?
Yeah. So by the way, I'm in the process of writing a sequence like daily tweets about each one of these four technologies. Okay. So T's, I don't like T's in the context of blockchains because T's I think they promise a lot but deliver very little, as opposed to MPC and ZK Starks that are based on very strong math. T's are not based on any math. They are based on engineering, on you trusting a chip provider, a specific chip provider, to do the following thing: to create a physical enclave, which is like a little chip. Think of it like it's a physical chip that will sit on your computer, my computer, a whole bunch of computers, and inside that, there are a variety of like hardware related assumptions. The most problematic from my point of view is that the chip manufacturer, like Intel, has printed inside that enclave a key, a secret key. And all of the security of the system is pegged on the secret key never being extracted. But the problem is, in the context of blockchains, that it is actually very feasible because these are physical bits sitting inside a physical chip, and a bunch of smart chemists, physicists and whatnot, with a budget of, let's say, less than $1 billion, can find a way to take one of these physical chips and extract the secret key. Now, once you extracted a secret key, like basically when you're trusting the result of a T, you're trusting that the only thing that saw the secret key and is using it is that enclave inside. So like if DPRK, Lazarus Group, puts its hands on a T, and I'm sure they already have, and I'm sure they already broke it and extracted a secret key, they can participate in a decentralized blockchain and sign whatever they want. And they also can decrypt whatever they want and see whatever. So, like, I really do not like T's in the context of decentralized blockchains. They could be used on your personal computer, let's say, as part of your biometrics, because, like, you're not worried that DPRK are gonna. Well, if they actually do take your physical, mobile, then anyways you're screwed, or you'll find some. That there's a problem. But in the context of decentralized blockchains, as opposed to MPC and ZK, just don't use T's, don't trust these. They're usually there only as part of a security theater, okay? Because you're really trusting the party running them to, not abuse them. And then FHE is, first of all, it's the youngest of all of these technologies. Um, Beautiful math as well. It's the one part that I know more about MPC, ZK than I know about FHE. Um, FHE, again, does not give you integrity at all. It basically allows you to do the following thing. You, with your key, can encrypt your data, store it now on a cloud or in a blockchain in encrypted form, and you can ask the cloud or the blockchain, oh, please run, this circuit on like this sort of computation on that encrypted data, and then the blockchain or the cloud will do that. And what you get is a new encryption that only you can decrypt and see, the value. So I don't think they're terribly useful in the context of blockchains. They could be somewhat useful actually with cloud. Like, I store my whatever stuff on Google. I don't want Google to know what's on it, but I do want Google to run some computations on it. And it's useful in that context. But I think in the context of blockchains, they're not so useful because they don't offer integrity.
So you'd have to basically combine them with ZK in some sense.
If you want to, like, blockchains are all about integrity, really, like a new way to get integrity by like large numbers. So if you want integrity in everything you do on a blockchain, like, you don't want to trust this other party. So if you're going to use MPC or FHE, you're going to want to combine it with ZK. And with respect to T's, just do not use them in the context of decentralized blockchains. Just don't. Like, they're like, it's broken technology.
Interesting. Yeah. Okay. There is certainly a lot of MEV type infrastructure relying on TEs, but I guess we'll see how. I guess they're more engineering types as opposed to mathematician types. But okay, so let's
Yeah, for the MVV, I mean, someone is telling you, look, I promise you that I won't front run. And the way I'm going to implement is I'm going to run a T. So I don't really get to see what's going on. It's like inside the algorithm, something good is going to happen. But there are like so many trust assumptions about that party doing it. Like, for instance, is the algorithm they're running inside the T what they actually told you that they're supposed to run, as opposed to just, so again, I just view it as a little bit of, well, either you have very strong trust assumptions with them, and then they could just raise their hand and promise, or have someone from a big K4 auditing their software and telling you that they never front run or whatever. Or yeah, I don't think T's are needed or useful. Like all those teams that do this as part of MEV, if they were tomorrow to remove the T and say, hey, we promise we're gonna not front run, I think people trust them just as much.
Okay. I do want to get into history, where like how you got into crypto and Bitcoin, Zcash, and StarkNet. I do have a few more questions on ZK, and the one I'm interested in mostly as a Solana person is I'm not super familiar with how the hardware here works, but I do hear that there is a lot of today, and it seems like this is improving, but there is some nuance on the latency overhead and how the hardware needs to keep improving for these provers and whatnot. Like verifying is easy, but proving maybe takes complex hardware. How does that work today? What are the shortcomings, and like what should we look forward to in terms of improvements?
Yeah, so if you look at the time to prove something compared to just computing it, there is a factor of like 10 to 100x reduction in like throughput. Like it's harder to prove something than just to compute it. And that's fine and will always stay the same. Um, Here's an anecdote. For the past 10 years or more, I'm often asked by VCs and all kinds of folks, oh, here's a ZK hardware team. Should we invest in it? My answer so far has been, and still is till this day, not yet. And the reason not yet is because there's still so much to be done just by using common hardware, and things are like very operating like very, very good at very high scale. So we're not yet at a phase where, yeah, look, for any problem, if you throw dedicated hardware at it, you will, if you do it right, you will get whatever 10x, 100x improvement. That's the case also for ZK. I just think there's not enough demand for that right now. The costs of producing it are too large. And another interesting thing is, even like you want the technology, you want there to be a lot of demand, but also you want the technology to be like very stable already, and everyone to agree on what's important. So, before StarkWare proved to the world that what you want to use is like small numbers or small finite fields, everyone was under the assumption, I mean, outside of StarkWare, that like you need these huge like numbers to work with. And if you would build hardware for them, and the Ethereum Foundation even wanted to start funding some huge chip to like do like these ridiculously large snarks. I told them like that's not the way to go. Like you can do things with smaller numbers. So that would have been a huge waste of time. And actually, a number of hardware, ZK hardware companies started looking at that, and it was just money down the drain. By now, thanks to basically what the technologies that Stark were invented and then productized and used first, basically ZK Starks, everyone is now agreeing that what you want to use is things based on cryptographic hashes and on very small numbers like 32-bit or so on. That's like our new prover, we just released it yesterday, uses 32-bit numbers. Now these are very, very fast and efficient on CPUs and GPUs. So like there's so much that can be gotten just from using standard stuff, and I think that's still the route to go. So scaling, is not a big problem. These ZK things cost more, but like we're not yet at the demand level that you want to build dedicated hardware for it.
Got it. Okay, cool. Well, I learned a lot, and at least so far, but I have a lot more questions. So let's maybe get into how you first heard about crypto, right? You were in math. You obviously mentioned how you were at the Bitcoin conference and you were talking to all these folks, even from Ethereum. How did you come across Zcash? Like, what is the sequence?
Yeah. So confession. I know that people think of me as a cryptographer, but my buddies in theoretical computer science, and even when I look at myself at the mirror in the mirror, I don't see a cryptography. I see what's called a computational complexity theorist. So like I didn't do a lot of cryptography. I did a lot of like math related to algebra, finite fields, and stuff related to computation. Anyway, so I'm not really a cryptographer. I'm more of a theoretical computer scientist. I was doing, first of all, math papers. I held research positions at Harvard, MIT, the Institute for Advanced Study. And then I got this huge grant in 2008 from the European Research Council. It was like 1.7 million euros, and and I'm a theoretician, right? I basically there's a limited amount of pencils, paper pads, and laptops that you can buy for 1.7 million euros. So I started funding research into implementing the kind of complexity theory based constructions that I worked on previously. So I was implementing things called PCPs, again, not thinking of this as cryptography at all, and just, was chugging along with that stuff. And then in 2013, I was basically peddling, mostly at academic institutions, this sort of theory to practice stuff that I was doing. And here's the thing: the theoreticians, like the mathematicians, didn't understand the practical aspect and like why you're doing this shit. And then the practitioners didn't understand the theory part and like why did you ever think this thing would be practical or anyone would use it? And that was like, so, but I did it. I had funding for it until I gave that talk at 2013 that said basically, hey guys, for the first time, like someone said, hey, look, there's this ZK stuff that can solve both scalability and privacy for blockchains, and the code is coming soon. Um, so we already had built a bunch of these different kinds of engines that can deliver on this, and we partnered with a team from John Hopkins. In this was in early 2014. They had a previous paper that didn't quite have general purpose zero knowledge, but was addressing partially the issue of privacy for Bitcoin. And we came and said, look, we have like this perfect engine that can basically deliver ZK for any computation that you need. And then
Is this
we
Matt
built
Green?
this. It was Matt Green, Ian Myers, and Christina Garmin. They
Mhm.
came from John Hopkins. And I had on my team, we were four people. It was Madar Zvirza, Alessandro Chiesa, Eran Tomer, and myself, who were already building within something we called Skipper Labs, which was a lot of it, funded by this 1.7 million euros, building for many years already, the sort of general purpose engines, including compilers from C programs down to ZK snarks and to what ended up being ZK starks. We didn't call it then that thing. We didn't have the name for that yet. So basically, we said, look, we have the perfect engine and the know-how for how to build general purpose statements. So we can take and build something that really solves perfectly the problem of privacy for Bitcoin. And we wrote this academic paper, the seven scientists, and we published it in 2014. It was called Zero Cash, basically privacy for Bitcoin or something like that. And then Zuko reached out, and we co-founded the Electric Coin Company or sometime around 2014 or 2015. And then basically Zuko and then his brilliant, engineers and cryptographers took over and implemented so we had academic grade code, but the basically re-implemented and productized and made this whole thing that actually, works, as opposed to you can run some test and show that it sort of works. And this was launched in 2016 as, Zcash.
Wow. Okay. Um, okay. I'm gonna give you the tall task here of explaining how Zcash works, right? So we talked about the conceptual understanding with the receipts and the polynomials, but like when I deposit money into the shielded pool and when I spend it, how exactly does the ZK work there end to end? Like, how can
Yeah.
I, as a layperson, be confident that my privacy is actually functional?
Yeah. So let us start with how Bitcoin works because basically transparent Zcash works just like Bitcoin. So we're in what's called the UTXO model, which means that everything is sort of it's like all the transactions that appear are sort of transfers of titles or of deeds, titles of uh, entitlement to coins. So let's suppose I'm paying you one transparent Zcash, which is the same as paying you, let's say, one Bitcoin. So what I'm doing is someone in the past, either through mining or someone paid me that. So there's something that basically says, here's a public key. I happen to own the private key for that. And then there's a number. Let's say it's one. I have one Bitcoin or one Zcash. And now you send me, or on your website, I found your public key. So now what I'm doing is I'm saying, hey guys, first of all, notice that there's that transaction in which my public key appears. Notice I have there one Bitcoin. Um, I would like to transfer it to this new public key that is yours. So what I'm going to do is I'm going to sign with my secret key that only I know. Something that basically says all of that. So it's like I take the hash of like my public key, the one Bitcoin that I have, your public key, and basically I'm saying, whatever, transfer it and hash of that, I'm signing. Everyone reads that, and now they sort of know that. Okay, this is how things work in Bitcoin. In Solana and Ethereum, a little bit different with accounts, but basically everyone gets to see everything, and that's of course the problem. So when I explain Zcash, I always say there's an easy part and a hard part. The easy part is privacy. The hard part is integrity, and that's where the ZK comes in. So how do we solve the privacy part? We just sort of encrypt everything. So instead of all these fields that we said that we have there, like your public key, my public key, the previous transaction, let's just hash each one of them or just encrypt each one of them. So now no one except for me and maybe you know that that's the information. So just imagine now a transaction comes on chain and basically you see some encrypted shit. Okay. So like intuitively understand, like, okay, now you can't understand. You can't connect the dots. You don't know what's inside this sealed envelope. But
Mhm.
now the real problem emerges. It's the problem of integrity. Like there's no central bank that we all send the information to and it decrypts it and operates. No, there are these miners out there. They need to know that whatever encrypted shit, these random bits that are going out there, there's like they have integrity. I actually have that one Bitcoin. I have a valid signature. Okay, that's exactly where the ZK comes in. So the ZK proves all of the needed things in order to make a transaction valid. And then what we do is we say to everyone, hey, I have a ZK proof that inside this envelope, you have no idea what's inside the envelope. The only thing you know is that it's valid. Now, if you want, I can go into a little bit more technical detail about how do we create the
Mhm.
envelopes and how do we solve the double spend problem. But at a very high level, you first of all just encrypt everything. Actually, you
Mhm.
hash it or you commit to it. And then you
Mhm.
use ZK to prove that what is shielded and what is encrypted actually has integrity and you're not minting yourself more coins, you're not paying money that you don't have, you sign things correctly because that's all about integrity, that the right thing is being done even when you're not watching. And ZK gives you that.
Okay, so that makes sense. So encrypt it and then use ZK for integrity in terms of, I mean, like the main problem that you're solving really is double spend. And the first iteration of, let's say, blockchain is we're going to solve the double spend by making sure everybody sees everything. And then now with ZK, you don't necessarily have to do that trade off. What is for the let's say
Could I
nerdier
just
people?
elaborate on the double spend because there is a very tricky thing here about double spend. Let me try. I'll just explain this. Right? Okay. I received. Let's suppose that I once a while ago I received one Zcash. Okay, and
Mhm.
but what the world saw is just this encrypted shit. Okay, but so I have this one Zcash. Now I'm supposed to be able to spend it. So why don't I do the following thing? I spend it once to you. Everyone will see some encrypted shit and a ZK proof that I actually can spend it to you. But then I take the very same Zcash and I spend it again, paying someone else, myself, let's say, and still have a
This
valid
is
proof.
where
Like this,
the
it's the new
nullifier comes
version of the double spend problem because exactly because like I am like each one of these transactions is valid because I actually, I can prove in ZK that I have this Zcash and I can spend it. So what prevents me? And everything is encrypted. So how does everyone get to know that I'm not double spending? And the simple answer to that is, well, we added one new thing inside each one of these sealed envelopes. There's a unique thing called a nullifier. Okay. And basically, the only thing, so it's like inside the envelope, but it's unique. There's only one per UTXO. And then once you spend, you expose to everyone the nullifier. And the double spend is prevented because every time I'm making a ZK payment, I have to expose a nullifier. And the consensus protocol will only accept the first nullifier, not the second one. So that's
Mhm.
how you solve the double spend when everything is encrypted.
Right. Yes. So it does seem like they did run into some scaling issues with the nullifiers being unbounded or not unbounded, but increasing in state growth. And Sean was working on something called
Yeah,
Project Tachyon
Tachyon.
to tackle this.
Yeah.
Um, what is okay? Let's the final part of this that I want to understand is how does the verifying actually work on the minor level? Like when you give me a proof saying like, look, I actually do have this, and here's a nullifier and all these things. When I verify that, like I have a hard time conceptualizing what exactly am I verifying? Like, how do I know what the inputs? First of all, I guess what are the inputs that go into verification? And then two, how do I know what they represent if everything is encrypted?
Yeah. So, okay, before going into the details, it's a little bit, there's a similarity here with just verifying, a Bitcoin or Ethereum or Solana transaction, which relates to signatures, right? All of these things, they use, your keys, your coins, and you're using public key cryptography to sign messages. So,
Mhm.
how do I like check a signature, and how do I make sure that when I'm checking a signature, like it does all the right things, right? And it's not that trivial, right? You need to make sure that all of the relevant information is part of what you're signing on, and then after the so a node would verify the signature, but then unpack the message and do all kinds of checks on it. Okay, similar thing happens with ZK. It's a little bit more complicated. The analog of the digital signature verification, right? There's a part of code that checks that the digital signature is valid. In the world of ZK, you call it a verifier. So it's a piece of code, cryptographic code, that receives a bunch of inputs. One important input, well, two important inputs are a statement, like that's the statement of like what transpired, and then a proof. So the verifier receives a statement and a proof and spits out one bit, yes or no, like I accept the statement or I don't accept the statement. Again, it's a little bit like with digital signatures. A signature, I receive a public key and I receive a message and I spit out yes or no, like is this a valid signature with this public key for this message? Sorry, I received three things. There's a public key, a message, and a signature. And I like spit out, do I accept it or not? So with ZK, a verifier receives a statement which claims this is what happened. And then there's a proof of the statement. And the verifier should check the two of them and spit out yes or no. Now, I think your question was how do we make sure that the statements are crafted in the right way to not reveal privacy but still maintain integrity? I could go into that for Zcash, but it's not that simple. Just like if you ask, how does a digital signature make sure that a Solana transaction is valid? I'm sure it's very complicated, like the details of it. So I could go into like making sure that the ZK proof actually, if you apply it to that statement, you get integrity of the system. You need to check the nullifier that didn't appear before. You need to check the ZK proof. There are a bunch of fields that are needed there, anyways. For maintaining, like there's a new commitment that you have to add. And frankly, since I'm not involved in Zcash anymore, I'm kind of blanking on some of the more gnarly details of that.
Okay. Yeah, yeah. I think there's a lot of complex stuff there. I tried looking into it, but next time. Okay,
Yeah.
so I mean, so now we have a good conceptual understanding of how ZK works on multiple levels of abstraction, as well as how Zcash works. Now, this was in I forget the exact time now. I
2016,
guess
I think it was launched.
2016. How did what happened next? How did you end up finding StarkNet, StarkWare? What's the difference between those, etc.?
Yeah. So even when we were working on the ZK engine that went into Zcash, which is called ZK Snarks, um, I was in love with a different area of cryptography and math that is far superior from a mathematical point of view. And that's what led to ZK Starks. So the T in Starks stands for transparent. There's no toxic waste or no like secret keys that are, appear in when you construct Snarks. Starks are also post quantum secure. And the real reason why I love them and believed in them so much, even before they were so popular as they are today, is because they are extremely fast and agile, because they don't have any of this sort of number theoretic or elliptic curve cryptography that is very cumbersome and has a lot of attached strings, which makes it also quantum susceptible. So there was this other branch of math that I deep down just always knew that it's the best kind of technology for scaling, also for privacy, but for scaling. And I was just infatuated with that. So I pushed it forward. It culminated with a bunch of breakthroughs called the FRI protocol and the ZK Starks paper. And a lot of it due to the sort of pedigree that had to do with Zcash. I could relatively easily um, co-found StarkWare, because like people said, "Oh, this is a guy that was already with Zcash. It's not just some crazy professor. This stuff actually works." So I think so I owe so much to Zcash in so many levels, but part of it is also that it really, really helped uh, found StarkWare. And of course, Zcash itself was one of the early investors, and but I always believed in this other branch of cryptography that led to ZK Starks. That's post quantum secure, higher scale, better speed, no trusted setup. And once I got an opportunity, I co-founded StarkWare in order to solve the problem of scaling and privacy, but scaling first.
Okay. All right. So let's get to StarkWare, StarkNet. What is so it's I'm a bit you guys have moved around here. I think it was at first an Ethereum L2. Now you guys are doing more Bitcoin stuff. So first of all, it's a roll up, it's a ZK roll up. Um, what is the motivation for it? Like what is the set of problems that you want to solve? What is the vision for how the network evolves? And then like how does it work in terms of your future vision with Ethereum and Bitcoin?
Yeah, so the very long-term vision is that this is the right technology in order to reach global scale, and in which you can truly own your life in a decentralized way. And the reason is everything on StarkNet is basically backed by these Stark proofs that assert integrity. And basically, what you get is like the best of both worlds. You can allow any party, which doesn't have to be trusted at all, to take as many transactions as it wants and just process them. But then you will know that this processing was done with integrity, because that party will just submit a Stark proof that everyone verifies. So you can have basically parties, let's say, running a perps for a day, and you can go there for a day if you want, and you can go there for a day, just send your transactions. You know that you won't be scammed or rugged, because like there's a code for what the perps exchange does, and you don't even care who operates it, um, because like basically the integrity of the Stark proofs allow that. So like there's at StarkNet at the end of the line, there's this immense scale to be had. Now, initially, when we started our very first systems, which actually were called a slightly different name, there was a huge scaling problem on Ethereum. Gas prices were, spiking at $40 per NFT, and we helped a bunch of clients to reduce their costs by factors of 20,000x because of this technology. So DYDX, for instance, was the best perps exchange at the time, running over our technology when everyone was like bleeding dollars and gas on Ethereum. They had the best user experience, which led them to being like highest volume perps at the time. Same thing with Immutable X with NFTs. Okay, fast forward. Now, today, StarkNet is the best ZK rollup on on Ethereum. Has the lowest cost, the highest scale, the most compute. But frankly, there are like 200 rollups on Ethereum. And anyways, Ethereum is slightly going down the Solana route of like getting bigger machines for validators. So like there seems to be less of a scaling problem there. On the other hand, Bitcoin has a much bigger opportunity there, which is what we're trying to tackle now. And that is the problem of financialization. Bitcoin, most of it, over 99% of it, is just being hodled, and less than 1% of it is being financialized, which means people generate yield on it, borrow against it, use it for all kinds of economic activity. But I strongly believe that with the right DEX platform, with something that Bitcoiners can feel comfortable with, they will want to generate yield and put their Bitcoin a little bit more into action. And that's exactly what we're now offering on StarkNet. So we want StarkNet to be what we call an L2 squared, which means we settle onto Bitcoin and onto Ethereum. But now most of our focus is on financializing and helping the financialization of Bitcoin. We want to expand Bitcoin GDP and expand the Bitcoin economy. And we're already offering this. The thing behind me says BTC-Fi on StarkNet already exists today. Bitcoiners can, I don't know how many Bitcoin listeners you have among your in this podcast, but those who do have Bitcoin and want to participate in operating StarkNet, which is a decentralized financialization layer for Bitcoin, also generate yield while doing so. So please check it out. There's a bunch of opportunities. You can borrow at the cheapest rate against your Bitcoin and use it to invest in a whole bunch of things. So our mission right now is to expand Bitcoin GDP using this technology that allows for Bitcoiners to have a very safe and self-custodial experience while having, very good UX, good yield on their Bitcoin, safety, maturity, scale, cheap costs.
Got it. Cool. Yeah, I will give it a try. I do want to ask you, with the last few minutes we have, some spicier questions. Okay.
Okay, I
And
love it.
um, and the way I want to frame this is, I'm an angel investor in crypto, and so like obviously I love Solana, and I'm going to build on Solana with my main company Helios. However, I do invest in other ecosystems, and so like sometimes I'll get questions from builders, which will be like, okay, do I use ZK Sync or do I use StarkNet? And so that's going to be my first question, which is like, what would you tell to potential builders on like why they should pick this ZK solution over other ZK solutions? And then number two is going to be some of the rollups that are most successful on Ethereum today are like optimistic rollups, right? Something like a base, where like obviously they have the Coinbase advantage and stuff. What would you tell to builders who are maybe on base or trying to build on those rollups about why they should pick StarkNet?
Okay. Um, why I would answer with a question. Why are three of the top perps exchanges among the top 10 um, built on our technology? Why is it that the only things that actually surpass in volume and TVL, those perps, are basically running on a centralized computer that proof of authority? And the answer is that giving scale and massive computation as is needed on something like a perps exchange is something that is very hard to find. So you cannot find it on Ethereum. You actually cannot find it on Solana today. You cannot find it on any of those L2s that you mentioned that are based on the EVM model, because the EVM has, compared to StarkNet, very limited compute. So if you want massive computation, which is needed for a lot of advanced DeFi at a low cost, StarkNet is your only option. This also explains why I know that like everyone sort of, as a Zcash co-founder, I'm very happy that Zcash is now in everyone's attention because people were fading it for so long, right? Here's another area that's being faded, but actually I have very high conviction will have a comeback. Blockchain gaming. Okay, everyone's fading it now. Yeah, it's not going to happen. Whatever. Well, I have 100% conviction it will have its time. A lot of the most advanced, fully on-chain games are being built on StarkNet. People don't know this because most of people just think that, there's no more blockchain gaming and no one cares about it. Well, people didn't care about privacy until, folks like you and others pointed out that actually it's important. And now everyone's talking about it. Gaming is being built on StarkNet and is far better than on any other of these infrastructures. Again, for the same reason, you have massive compute. We are today running at a level of 2.6, like this is like actual numbers that happened. We already had 2.6 thousand user operations per second as our max. We're number one in terms of maximal user operations per second, which is a better metric for basically compute velocity. Just to explain that, like on StarkNet, you can take what on other chains would be broken into many, many different transactions, small ones, because there are limits on the size of compute. And you could put all of them in one. So like if you have some multi-collateral settlement on Extended, which is a leading perps exchange built on StarkNet, then it will translate into, dozens or multiple transactions, user operations. Okay, so massive compute. If you want to do new stuff, so StarkNet is your only option. Another thing is, if you still believe in decentralization, if you're fine with basically trusting Coinbase with everything, okay, that's fine. But I think a lot of the developers don't want that because they understand that either, tomorrow, because of corporate needs, or if not that, then whenever the Democrats come back in power and decide to take it out on Brian and his folks, it won't be fun to be building on base, right? Things, will just be blocked. You cannot do this, da da da. I mean, just recently we heard that, like, France put in prison Pavel from Telegram, and suddenly, a lot of like French Telegram users get. Does anyone have a doubt that this will happen again at some point? So if you want centralized, sure, but then you don't really need blockchain. If you want decentralized, StarkNet is the only L2 that is actually making concrete steps towards decentralization. So decentralization and then massive scale for compute are the two reasons you want StarkNet.
All right. I love it. Excellent. Very well said. Okay. Well, two final questions for you. One will be advice for people who want to learn more about ZK as students of this new field, let's say. What would you advise them start with or look into, books, whatever it might be? And then two would be, how can people get started with StarkNet?
I think both questions, same answer. Follow me, follow on Twitter, follow StarkNet, follow StarkWare. One of my pinned tweets, or I should retweet it again, is a bunch of links that explain everything from simple to complicated about ZK Starks and how StarkNet works. But basically, if you Google, follow me on Twitter, follow StarkNet. There are a lot of links, and I'm happy to share. I don't know where on this podcast, I'll share some links, starting points for reading more about ZK, about StarkNet, about your first steps. For StarkNet, it would be starknet.io. Then there's a bunch of resources there.
Okay, cool. Yeah, I'll add that to when we send the podcast episode to a follow up tweet or something. All right, excellent. Well, Ellie, thank you so much for the time. Thank you for coming on, and thank you for your work in the field.
Thank you, Mert. Thank you. Enjoyed this tremendously.